by then and see what's going on.
All right. No, we should be good.
Okay.
The mics work. That's all we really need. Thank you.
Is it Mike?
Yes. Yeah,
We
that's,
set these up so you're not paying attention to the screen. You forget where the stairs are.
yeah. We've had somebody. I have a little mishap here once, so we'll put this for you.
And if it makes you uncomfortable or whatever, you feel free.
I'll be fine.
Oh yeah, I know. Ready?
Yep.
Okay. Good afternoon, everyone. May I have your attention, please? Okay. Our speaker today is Michael Campbell. He is the director of the Energy Division of Logos Technology, headquartered in Fairfax, Virginia. He is responsible for all of the energy activities within Logos, which include programs to develop cellulosic feedstock into ethanol and biojet fuel, to close the nuclear fuel cycle in advanced reactors, and in physics of fusion. His research has included the development and application of high-power solid-state lasers, nuclear energy, fission and fusion, plasma physics, hydrogen production, and energy, including biofuels. He is the winner of numerous awards, including DOE's E.O. Lawrence Award, the American Nuclear Society's Edward Teller Award, and the American Physical Society's Excellence in Plasma Physics Award. Campbell received his undergraduate degrees at the University of Pennsylvania and advanced degrees at Princeton and the University of Western Sydney, where he received the Doctor of Science degree. Please welcome our speakers.
Well, thank you. I also play the guitar and draw, so blues is the way to go. So I'm going to talk about sustainable energy for the 21st century. My background is somewhat interesting. I started off in fusion research. I still do a lot of fusion research. You know, when I was undergraduate and graduate at Princeton, I was motivated by the wars in the Mideast in the 70s, and all of a sudden I remember standing in line in Princeton, New Jersey for gas on the day that an odd day since that my license plate ended in an odd number. Many of you probably don't remember that, but it left an indelible impression. So that motivated me to get involved in energy research, fusion. And when you do fusion, you find out that fusion is still a long ways away, but eventually we'll get there, and I'll talk about that. But over the course of my career, I've gotten involved in fission. And when you first do fusion, your first opening statement is, it's not fission. And I think that's a mistake by the fusion community, because it's just wrong for lots of reasons, which I'll talk about. I also got involved in transportation fuels.
So that we can
Sure.
record it. Sorry to interrupt you.
Okay.
You should flash through.
Is that right here? Okay.
Turn the lights off?
Sure. And so that's why, and biofuels and the like, we'll talk about all of that. So there is no one golden bullet or silver bullet to kill the werewolf. Energy, we need lots of different things. Diversity of sources is critical, and that's what I'm going to talk about. So we'll be talking from nuclear to biofuels, all related to the sun in some fashion. All right, so here's an outline. So I'll talk a little about Logos. I have a colleague and good friend here, Gus Moore, is an alumni of this great university. Stand up, Gus. There he is. So it's not just me here. I want to talk about Logos. How's a company that get involved in such a diverse range of things? Then a little motivation about energy, which many of them I'm sure you've heard many times, but it's always good to hear it again to get you motivated to keep on looking at these things. Then talk about nuclear energy, both fission and fusion, and biofuels. All right, that's the outline. What the hell happened here? This went up too fast. There we go. There we go. So Logos. Logos is a small company. It's actually, many of the people are from some of the national laboratories, from Lawrence Livermore Laboratory and DARPA. So a lot of familiarity with federal research and how the money flows and what it does. We're in Ashburn, Raleigh, North Carolina, Livermore, Visalia, and in Fairfax. We have a biorefinery up in the great part of California in the Central Valley. Not all California is a paradise. The Central Valley is unique. We have a biorefinery up there, which let's see, does this work? Yeah. That still works. Never trust lasers. That's our biorefinery up in Visalia. It's a 2-ton-a-day cellulosic ethanol plant. We have 4 divisions, and we're involved in a lot of intelligence, surveillance, and reconnaissance technology. That's a lot of the company is actually working to develop the technologies of fighting wars against individuals. So we have a lot of systems deployed in both in Iraq in the past and Afghanistan today to try and help our soldiers protect themselves and watch what the Taliban and their allies are doing all the time. It's another interesting talk that Gus and some of those things that you should hear about sometime, because it shows you how modern wars at least are going to be fought. and they have been fought. So one of the things we do with persistent surveillance, this is basically Google Earth at 1 hertz watching a city. So we watch a city constantly to look at bad guys, where they go, what they do, and where they come from, and where they go back if they've done it. So it's a very interesting thing. You'll see a lot of that in the news, protecting the soldiers against IEDs and other various nefarious things. I'm going to talk about energy systems, which we do, biofuel, nuclear, and high-powered laser technologies. I'm not going to talk about lasers very much, a little bit, but we do that too. And then, of course, we also look at supplying intelligence people, looking at things like cybersecurity. So it's a broad range of capabilities, about 200 people, a lot of clearances here, so you get to see what the government really is thinking or what they should be thinking. And of course, in science, engineering, lots of different technologies. So it's an interesting company. I've worked at a very large national lab, Livermore. I worked at a very large privately held company, General Atomics, and this is working at a small company, has its challenges and opportunities and flexibility. All right, that's Logos. Gus, you want to say anything about Logos? All right. Okay, let me talk about motivation. Now we're going to talk about what we're here for. I always like to show this because it shows you all the diverse ways of energy is used, from airplanes, to powering, lighting up the world, from driving around, from factories, from shipping, from rail, and manufacturing. There's a new TV show, one called Revolution. I don't know how many people watch that. Somehow the world has stopped making energy and is seeing how the world reverts back quickly. It's an interesting TV show. But it powers the planet, and it's very, energy and quality of life are correlated. No surprise. And there's a thing that was developed by colleagues at Livermore and elsewhere called the Human Development Index, HDI. And what it does, it's a way of trying to quantify the correlation of quality of life and energy use. It has things like life expectancy, literacy, educational attainment, GDP per capita, all those things wrapped into a way of looking at things, which is, of course, and that's what it looks like. When it's 1, you're doing pretty well. And you can see who's up 1. There's Canada. It's cold there like it is here. US, all the G8 countries here. About 1 billion people are tied up in here, and around 6 billion people are tied in here. And it directly correlates with annual electricity use in kilowatt hours. This is a vision of what the future will be. I'll tell you about that in a second. But you can see China, India, where other parts of the world where most of the world's population is going to move in this way. They want to move up here. They're going to be moving this way. And let's just say they're as good as Japan, because Japan is a very energy efficient society, given its lack of natural resources. And they'll be up at 6,000 kilowatt hours per person. Right now they're basically a little over 1,000 and less than 1,000. So there's going to be a lot of energy growth over this century. I'll leave this question at the end, but this is the century of Fermi's paradox. Does it work on Earth, or is Earth an example of Fermi's paradox? We'll see who remembers what that is. I won't tell you. You can ask me at the end. So right now, as I said, the population is 6 to 7 billion. Electricity use is the total electricity use in gigawatt years. And again, most of the world's population is below 0.8, as you can see here. What's going to be in 2100? That's a challenge that many of us have to face. Some will face it more than we will, because I won't live to the end of the century. But some of you will be around near that, or your children will be. A population of about 9 billion people, hopefully stabilize. Have 1 billion still being relatively wasteful. Most of the people being in this range, and of course there'll always be those who are underneath. But it's going to be a lot more electricity than we have today is going to have to be found. And that is a motivation to continue to look and develop energy sources. And one of the things that we were having a discussion today about transportation, that's electricity. Here's an interesting thing that Steve Coonan put together when he was the chief scientist at British Petroleum about, transportation use is also going to go up as people learn, as they get more wealthy. They get more wealthy, they want more freedom, they don't want to run the bus or walk anymore, they want cars. And what this is just a simple thing of showing the growth in auto use as a function of income. Here's, public transportation goes down, walking goes down, cars go up. China's a big car market. They don't have the driving habits of the United States, but transportation needs are not going to go away. And of course, most of it's made by fossil fuel. All these things 80% today is fossil fuel. Here's an interesting plot also that Steve Coonan put together. Was, what is the U.S. energy mix over the past 150 years? We used to use a lot of wood, so biomass, biofuels is an old concept. And of course, as time went on, you see what happens with that, replaced by oil, nuclear, coal. And what the challenge, it will be when someone draws this plot in the beginning of the 22nd century, what does it look like? And so I'm going to talk about some possible options of what that mix could be. Again, just everything you already know. U.S. is 4.5% of the world's population, 21% energy consumption, blah, blah, all these things. So a lot of transportation, that's why biofuels is interesting to me. I'll never fly, this is a Dreamliner, you'll never fly that with batteries. You'll always be flying that with JP8 or Jet 1 and the like. So transportation is also going to be a big deal that we're going to transform over time, but we're always going to use hydrocarbons at some level. Now the U.S. Needs to be a leader in this, of course, because we are such a consumer of energy. And one of the things that we lack is we don't show a good world use in that. We have to be much better, and hopefully people here and elsewhere will help us be better. But of course, fossil fuels are not the answer. I worked at General Atomic. This is a predator. We fight wars over oil. I mean, who thinks the root cause of wars in the Middle East are anything but energy? They are. I believe that climate change does occur by anthropogenic influence on the climate, on the atmosphere. I believe that. And I think, hopefully one of these days it won't be a political thing. This is the ice sheets in Greenland melting away. And of course, the environmental consequences of energy go that you have to look at the entire value chain, not just the CO2 that's produced, but also the value chain in the beginning. So we have to get away from fossil fuels. I think everyone agrees with that. The question is how and how long, what and how long will it take. Here's an interesting thing that I always like to ask people. How much power does the world need? If you were God or someone who could create, all you need, what is an asymptotic limit of what the planet will use in terms of power? Right now we're about 13 terawatts of power. The instantaneous use of the world is about 13 terawatts. What do you need, and what will the future be? So here's an interesting thing that Freeman Dyson did a long time ago, to show essentially what happens with compound interest for a long time. So here it is, forget this for the time being. This is years from now. What this is terms of the power level that we'll need. Right now, the Earth is 12, 13 terawatts, trillion watts. If we grew at 10%, 2% a year, we would basically become a planetary type system, which means pretty soon we'll be producing as much power as the sun puts on us, which is about 50,000 times what we're doing right now. That'll never happen. If we keep on going, eventually we'll outshine the galaxy. So it won't happen. The question is, when does it stop? It's a good question to think. What will the world eventually need when we stabilize the population at 9 or 10 billion, and how much power and how much energy will the world need to be sustained? And my own assessment of that, it's going to be 25 to 50 terawatts. 50 terawatts would be too much, but somewhere 2 to 4 times what we use right now is what the world can sustain. And of course, there have to be adequate fuel supplies. It's got to be renewable. We can't just take away what nature gave us for hundreds of millions of years and take it away in a few hundred years. It needs to be abundant, of course. Flexible electricity, transportation fuels, water, process heat. The two great qualities or the problems of the next century are water, food, and fuel. Water is a major issue. Of course, I live in Southern California, and although the ocean is 8 miles away, water is very expensive for me. So California spends more money moving water around than any other commodity. So these are the things that you have to look at when you look at biofuels, for example, and actually anything. Right? Go back. Sorry, I'm still not getting used to this. And then the other thing, of course, it's got to be consistent with the environment. I think everyone who's sensible believes that. Economics is a function of time, of course, at some level. And consistent with political realities. If you're going to do nuclear power, you have to worry about proliferation, waste. I made this up before Fukushima. And people, of course, Fukushima has left a big, indelible, negative impression on much of nuclear. For central power from coal, sequestration, I'm not a big believer in that. I think that's an enormously difficult problem and have a lot of political unacceptabilities. And of course, biofuels, solar, wind has to compete with water, food, and land. So now I'm going to talk about nuclear energy. I started off in fusion, and I still believe that nuclear energy, including fission, is a way to go. And I'm going to talk about a reactor that doesn't exist at scale, but I think will meet many of the needs to make full-scale nuclear deployable. All right. So why does anyone like nuclear? I think you've had some speakers talking about thorium, and the obvious interest. This little fuel pellet has this much energy contained. It's why nuclear explosives are so deadly. 1 million times more energy per gram is released. So there's a lot of energy there. Excellent safety record. I would have said that before Fukushima. But remember, Fukushima was a 1960s reactor designed in a way and placed in a way that no one would make sense today in hindsight. It's like Chernobyl. Chernobyl would never have been licensed in the United States. Our nuclear reactors have a very good safety record. 3 Mile Island would have not have had any incident if the operators not turned off the safety systems. Economically competitive, well, that's the big challenge right now with natural gas being what it is and all the regulatory things still with nuclear. But it has a chance to be this, and the reactor I will show you can be extremely safe. And next generation reactors can do a lot more than just make heat or make electricity if they need. I'll show you that. And of course, there's a lot of fuel around, both uranium and thorium. Thorium is a good fuel. It's been used in the past and should be used in the future. And of course, it is the greenest of all the energy technologies in terms of its GHG emissions, and if you look at the life cycle. This is an old thing from National Geographic, which shows the carbon intensity, if you will, as a function for different materials. And nuclear is far and away, this is the carbon intensity here, nuclear is far and away the life cycle cost, and that means mining, construction, of any of the energy sources you have. Again, this is looking at the life cycle cost of these things. France, remember I told you my career getting back involved in fusion with the wars of the 70s that spilled over in our energy stuff. Well, France, two things happened. The US got DOE and France got nuclear. So who won? France won. So this is an example of, let's go back. The large-scale deployment of nuclear happened in a relatively short time in France. You see the distribution of power. Nuclear takes about 80% of base electricity in France. Sell some to the Germans if they want to get rid of nuclear. In terms of its CO2 and dust, large reduction that of course corresponded with a reduction in coal and natural and other fossil fuels, and the other difficult things. So sulfur dioxide and stuff like that all went down. NOx, all these things went down on the event of nuclear, and they did it in a relatively short amount of time. And I think it stands as an example of when you make a national policy you can affect. And this was not just building electricity for a few places, it was for a modern country. But why not nuclear? That's probably just as easy to say, right? Why not? Well, each gigawatt reactor annually uses about 22 tons of uranium. The spent fuel is mostly uranium, U-238, but there's about a ton of fission products and about half a ton of the transuranics, with mostly plutonium, what people worry about. So of course, that's considered, this causes this causes that. And of course, anyone who doesn't like nuclear always brings those things up. And of course, you had catastrophic accidents at Chernobyl. And again, that was a reactor that never would have been licensed in the United States or any modern country, only the Soviet Union. I was one time up in St. Petersburg, or Leningrad it was at the time, and they had a Chernobyl-type reactor about 10 miles away. And I'll tell you, I was nervous the entire time I was there. I wanted to make sure they weren't doing any tests. And then Fukushima. Now, Fukushima was quote a modern reactor, it's a GE reactor, reactors, but designed in the 60s and then deployed in a way that was not, let's just say, ready for the catastrophe that the tsunami caused. I live in, again, Southern California, and San Onofre is a nuclear power plant about 50 miles from my house, right next to the ocean. So I get a little bit concerned, but we don't have the same faults in California as they do near, at least in Japan. But you have to be worried about that, of course. And then, of course, the other thing is proliferation. I don't have to tell you about how many times Iran is in the newspaper about enrichment and making nuclear materials that can be transported into nuclear bombs. Now, the Manhattan Project, everyone knows that in World War II. It's about $2 billion spent in those dollars at that time, which was a pretty amount of money to reconstruct the auto industry in some fashion. Only $70 million was spent on the science. $1.93 billion was spent on making the materials. So it's all about materials. And one has to always be concerned about that. For central power production, coal, I don't think coal is the answer for lots of ways. It's an environmental disaster. And the faster we can phase it out, the better it will be. Natural gas is doing that now. It used to be 50% of our electricity was coal, now it's only 35%. And it will continue to decline. I was doing some work for a nuclear company trying to see what the nuclear renaissance would be. And it turned out that the nuclear renaissance had many opponents, as you would imagine, but the coal renaissance had even more. And so it's very hard to build new coal plants. And so it's not going to be base electricity, it's not going to be coal. All right, wrong way. All right, so here's a view of what the future could be with nuclear. So let's start off with, we want to stabilize CO2 at about 550 parts per million. So it'll be warmer. You guys won't have such severe winters. I'll have more severe summers. But that's something that you're not going to freeze it at 400 parts. It's impossible given the inertia in the system and how long it takes to do. So let's put a goal at 550 parts by the end of the century. Could I do something could I have a mix of energy technology that would allow that? And the answer is yes, but it does involve a lot of reactors. Right now there's about 400 nuclear reactors in the world. This would involve around 4,000. And obviously one has to do a lot of things to make that happen. It's not going to be the reactors we have today. If you do that, you actually could have, here's how you look at where GHG stuff comes from. You can see if you do that, you can actually, I won't go into the units here, but I mean, it becomes the biggest area in greenhouse gas emission will be transportation, if you're able to do something like that. So, of course, here what you have to do now is make hybrid vehicles or electric cars and much more efficient autos. So it's possible that you can actually switch electricity from being the main source of greenhouse gas emission into one which is a minor player. But you're going to have to do something which involves making lots of reactors, I think. All right? And there's that. So if you want to do that, what do you need? You need a reactor that, if I asked all of you, what are the things you don't like about nuclear? I'm sure everyone would have a different one, but they'd probably all have these 4 categories. It's got to be safe. You can have a meltdown, because the consequences of a meltdown and a breach of a containment is catastrophic. Ask the Japanese, ask the Russians, ask the Europeans. It's got to be very efficient. That means why that? You minimize the waste. Every watt of nuclear power should go into something useful. Right now, only a third of it does. Only a third of nuclear energy goes into making efficiency of electricity is very ancient. Steam cycle is very inefficient. Versatile, which means it can be big and small and can make different products. And of course, you want to minimize the waste. That's what the future nuclear reactors have to be. And I'm going to tell you one which is some of you may know, and hope more of you will know by the time I'm done. So this is a reactor that I worked on at GA, and I continue to work at variations of it at Logos. And it's a high-temperature gas reactor. Now, who has ever heard of this? It's a great reactor. And I came in with fusion thinking fission sucks. And I came away thinking, this is actually not bad. 80% of what I like in fusion this has. Why do I like it? I like it because the fuel is not metallic coated, it's ceramic. Ceramic fuel. Each one of these little things you'll see in a minute are about a millimeter in size. Here's a nuclear material, and it's surrounded by ceramic, which acts as a pressure vessel. So all the fission products are contained within this little thing. There's many, many, many of them in a reactor, but they enable you to basically keep the fission products very much away from the environment. It can burn spent fuel. It can burn its own waste. And that's a nice thing, because if you want to minimize waste, it can burn its own waste, the TRUs. It can burn plutonium from the weapons program. There's a program at DOE actually which is to use this reactor with the plutonium core to burn up Pu-239 from the weapons program. And it can do thorium. It can burn all these fuels, and it's exactly the same reactor. The only thing that's different is the kernels inside this TRISO fuel. And the other thing about it, the coolant is helium. So vent helium to the atmosphere, no problem. It's not radioactive. A lot of helium. With all this natural gas, we got a lot more helium than we thought we did a couple years ago. And it can make electricity, process heat, can do hydrogen. It can actually be an energy source for biofuel production and the like. So this is a reactor which I think, and I'll tell you more about it, that hopefully in a number of years there'll be many, many, many of these things. So here's what this fuel looks like. This is the fuel, and there are a bunch of layers here basically. And again, just think this is a pressure vessel. And the kernel, that's the fissionable materials, uranium, plutonium, thorium, or actually the TRUs. It's the size of it, goes in compacts and goes into block and a core. It actually can go into not blocks and go into pebbles. There's a thing called a pebble bed reactor, which is the same reactor but just a different geometry of the moderator. So the moderator is a thermal reactor. So the moderator is either graphite or silicon carbide. Here's an example of what these things look like. They've been done, and they've been made in the past, and they're being made today in China and Japan. Here's the fuel again. This is the pressure vessel. You can make them big or small. This is a plutonium core right here. All right. These things are passively safe. What does that mean? It means if you lose the entire coolant, nothing happens. The reactor has what's called a negative temperature coefficient, so the fission slows down. And loss of coolant, the reactor decay heats away and nothing happens to the fuel. The reason for that is over here. This is what this is the particle failure as a function of time when it's heated to different temperatures. 1600 degrees C, 1700, 2100. What you do is you design the reactor so that the complete loss of coolant, it never reaches temperatures above 1600 degrees C. That means you can isolate from the environment, you can plug up all the air ducts, you can lose everything, and nothing happens. I've gone to China. They have a reactor in Tsinghua University. One of the tours is a catastrophic loss of coolant. That's what they do as a tour. It's a university, and that's what they do. And these are the maximum temperatures it gets to. This is when it loses. This is when there's you still have coolant. Here's when you completely depressurize no coolant, and here's where you shut off everything. And it's also buried in the ground, which is a good thing to do in modern reactors. So it's designed to be passively safe. That means you would not have to have an evacuation outside the site boundary. Major thing if you want in the future. Right, wrong way. In addition to that, the temperature, if you want high efficiency, remember, every watt of nuclear fuel or power you make, you want it to be used. Maybe right now, only a third of it is used from thermodynamic arguments. So here's the typical temperatures. So the output temperature is the key. The typical temperature for light water reactors, which is what we have today, it's about 300 degrees C. So when it's done cooling or making steam, there's not much leftover energy to use. Take a bath in it, but you can't do much more than that. So you can't do cogeneration, you can't do lots of things. Fast reactors, these are reactors which have things like sodium moderators, and I won't talk about these are the breeders. Their temperatures are 5 to 700 degrees C, so they're hotter, they can do more things. The gas reactors can be above 850 degrees, and they can run up to 950 degrees. So that means you can do a lot more things, not only in terms of higher efficiency, you have more applications, you can do cogeneration, and actually you can air cool these things. You don't have to have them by a place of water. The temperature differential between the atmosphere is so high, you can actually air cool them with very little loss in efficiency, which means you can put it out in the deserts, which you can't put nuclear reactors now, or places where there's not much water, because water is a key, as you know. If you do this, here's a typical reactor in terms of just a little pie chart to show you. Typical reactor is about 33% efficient, uses a low temperature steam cycle. That's what we do today. So all this nuclear heat makes waste and has to heat the atmosphere. It doesn't do anything else. If you do this with a high temperature reactor, you can make power at almost 50% efficiency with a Brayton cycle. Right? You have the chance to do gas turbines. You can use process heat for making biofuels. You can make hydrogen, and you have about 25% loss. So you're using almost 2.5 times the efficiency of making nuclear heat is useful work. And that's very important if you want to have, save the planet. It also comes in different sizes. This is a 600 megawatt unit. This is a 25 megawatt thermal unit. So this would be about a 12 megawatt electric. And there's a lot, I'll show you a little bit later, there's some interest in the military for these small reactors. DOE now has a program to make small modular reactors. And we had done this over 10 years ago trying to sell this. But it's the same reactor, just a different way, a number of core, amount of material, and how you arrange the core. But it can be very flexible for site size. If you want a gigawatt, you put 3 of these together. Another important thing is because the fuel is encased in ceramic, you can burn it up. What means this, ceramics are neutron resistant, radiation resistant, far more than metal coatings are. So one of the things you always look at in a reactor is how many megawatt days per ton of material, how much megawatt days of energy per ton of heavy metal do you use? Light water reactors are about 50,000 megawatt days per ton. That's what you get. This is data from 750,000 megawatt days per ton burning plutonium up. And this was done at a US reactor in the 70s. Here's one with the thorium cycle. You have to show your friend there's a thorium cycle here, which is almost 200,000 megawatt days per ton. So you're much more using up the fuel, and that's getting more energy out. Very important thing in terms of looking at utility of reactors. And actually, this is part of a U.S. program. I mentioned this before, a non-proliferation program to burn up weapons-grade 239, plutonium-239 that the Soviet, Russia has, and we have, is to burn them up in these reactors. So, and you see how well they do. And of course, this is waste. So leading on to that, you can have a reactor. And we have designed reactors, we call them deep burn, and I'll explain that in a minute. Very simple. 80% of the reactor is uranium, And the 20% of the reactor is its spent fuel. You have to have one reprocessing step, and you can't do this without reprocessing but one step alone. And if you do that, you can, I'll show you what the impact is in a minute, but this reactor can actually destroy its own waste. And not only that, Yucca Mountain, remember all Yucca Mountain? Yucca Mountain, we spent $13 billion on it. Now Harry Reid, being senator from the great state of Nevada, says it ain't coming here, and it's not going there. So who knows what we're going to do, is put it in spent in caskets for the next 100 years, but eventually we'll have to do something. And this was just a thing that we made up a long time ago, that if you were going to put it in a repository, this is again, here's our kernel, here's our fuel, it's in a matrix and then a block. What you have here is these are all the radioactive isotopes. Function of time. One of the problems that Yucca Mountain had was the storage mechanism they were going to do, the metal cladding fuel, was predicted to fail between 10,000 and 100,000 years. I mean, give me a break. We ain't walking around, but all a lawyer needs to do is say it's going to fail sometime in the future, and that's all you need to have the legal system say it's not going to work. Hopefully, 10,000 years will be a lot smarter than we are today. But the reactor, this type of reactor to fuel, tests that were done, with accelerated aging, would mean that it would fail well into 1 million to 10 million years in the future. I mean, we had almost had, not to have dinosaurs then, but we had very interesting mammals 10 million years ago. But by that time, all this stuff has decayed away. So you can actually make an argument to a lawyer that you have a repository that could be stable for the entire life of the material within it. And that's a big deal if you're a lawyer. So here's a way of looking at this. When you work on fusion, you have to look at a 100-year time frame. So here, this is a little bit complicated. Let me explain it. So the ordinate here is nuclear power in gigawatts. Right now, this would go up to a terawatt electric. Right now, the U.S. uses about half a terawatt of electric power at any one time. This would be twice what we're doing now, and hopefully that would be good enough in a century. You also do hydrogen, but that's, I'm not a big fan of making this much hydrogen. This looks at electricity. Function of time. If you did, and over here is waste. This is what the waste you generate. This would be a Yucca Mountain. In the old days, this is all Yucca Mountain could do. So after a short amount of time, you need another Yucca Mountain. And it's supposed to be east of the Mississippi, so maybe it would come to New Hampshire. I'm not sure. So here's the growth of nuclear power at 2% a year. Not too bad, building a couple of reactors a year, for a long time. In 100 years or so, you're up at a terawatt of power. So you're basically supplying all the U.S. electricity from nuclear. Now, unfortunately, if you did it while we're doing it now, this is the waste that would be generated, and you would need many Yucca Mountains over that time period. If you started phasing in these gas reactors I told you about, in about 20 years, you could actually, this is what would happen. So the waste would go down this way. You'd actually be able to have a Yucca Mountain for a long, long time, one repository. And actually, if you use some destruction, this is with fast reactors, but I'll show you this with fusion, it goes away. So you can actually produce it without any waste. So there is a chance of having a long-term deployment of nuclear that would satisfy safety, would satisfy waste, and it would be a very efficient energy source. What about proliferation? All right, everyone worries about the proliferation. So the interesting thing about this is that, let me go down here. Because it burns up so much of the fuel, because the nuclear cycle is so favorable, you produce very little 239, you produce a lot of 240, 241, which this is a poison in a nuclear. If you're trying to build a nuclear bomb, you don't get this stuff in it. So you have to separate the 240, 241 from the 239. That takes more sophistication. And actually you get a lot of 238, and so you have problem. This is the one for weapons. This is a pain in the neck because it's too hot, and this is a pain in the neck because of spontaneous fission. So you actually get material which is not very proliferation friendly. So even if someone could steal the fuel, they'd have a tough time making a bomb out of it. These things exist. That's one of the frustrating things, is they exist. This is one in Japan. It's a 25 megawatt research reactor. Runs at 950 degrees C. That's the output gas temperature. And today China is constructing a pebble-head version of this at the, I can't pronounce it, Shidwan project on the eastern coast of China. So not being done here, pioneered in the United States and Germany, and now being done in Asia. Now, maybe there's a chance to get the U.S. interested, and how's this? So here's an interesting thing. It was like, back in the old days when nuclear was, everyone liked nuclear, Admiral Rickover was one of the great man on Time magazine. So people associated nuclear with Admiral Rickover. Now they associate Homer Simpson with nuclear, right? He runs the power plant. So, but the 100 and so reactors we have today all came from Rickover's need to make nuclear reactors for submarines. At the end of World War II, submarines were going to become extinct. There was no need for them. We had aircraft carriers, projection of power, and submarines had to surface. They couldn't stay underwater long. They were easy to detect with high-resolution radar and very much like that. You can see periscopes and the like. So nuclear was developed. Rickover said we need a nuclear submarine because we want to be able to have a platform for nuclear weapons that is invulnerable to a first strike. And I know nuclear can do it. So a national security issue motivated nuclear power and submarines. And of course, there are more nuclear reactors in the military today than civilians. Did you know that? There's about 104, 105 nuclear reactors the military has today. Did you ever hear an accident? You know, they're in all the submarines and all the aircraft carriers are nuclear powered. And there's 2 based in San Diego. So every time I go down to the wharf, I look out and I see 12 nuclear reactors there that no one knows are there. But is it possible to get another motivation for the DoD to get involved in nuclear? And the answer is maybe. And here's a Logos design of, there's a lot of interest in the DoD for small reactors for forward operating bases and remote bases. Because it's very expensive to bring fuel to Alaska, and it's very dangerous to bring fuel to forward bases in hostile territory. And so the Army and DARPA is beginning to look at small nuclear reactors. And so, of course, we have designed a very small, hold on. We have designed a very small nuclear reactor. Here's the size of it. These are the different sizes here that you can transport in a plane or by heavy truck or heavy helicopter, to wherever you want. And it generates around 25 megawatts of electricity. It's a gas-cooled reactor, very, very closely coupled together, so the entire system is easily deployable. So we're exploring this with the DoD, and this may be a way of getting gas reactors onto the page of it in the United States. I hope so. Just to show what it looks like, here's one in a military base in Italy. You can't look at forward bases. Google Earth doesn't allow you to look at military bases in Afghanistan, so you can't see them. But here's one in Italy. This is a nuclear footprint. This is one that actually makes 15,000 gallons of JP8 a day and provides about 10 megawatts of electricity and process heat for the base, and that's the footprint on that. So we've coupled some of our biofuels expertise with a power source here. So hopefully I'll come back in a couple years and tell you about these things, and you'll see that maybe this will help nuclear get started again in the United States. All right, fusion. Now we'll switch to fusion. Fusion, the reactor I just showed you is a Gen 4, it's called a Generation 4 reactor. Fusion is a Generation 6 reactor. And that's how you look at fusion. That's why I look at that, connect it to fission. I was talking to some of the very good students you guys have here talking about, energy. All of them asked about when is fusion going to be here? And one of my things I always say is fusion and fission were discovered in the same decade. Do everyone know that? They were discovered in the same decade. Hans Bethe, it actually came out of how could the Earth be older than the sun? Because no one understood how could the sun radiate its heat for so long. And if you ever look at Charles Darwin's different books on evolution, you will see he got nervous about that at later editions about, evolution takes time, but the sun can't burn for more than a few hundred million years from gravitational collapse. They had to figure this out in the 30s, won the Nobel Prize for it. And Lisa Meitner figured out Otto Hahn's and Strassmann's experiments in a 1939 German laboratory. Big difference. One, nature gave the clue, and the other one, man figured it out, or a woman figured it out. She got the Nobel Prize for it. And within 3 or 4 years, you had nuclear reactors. Right? You had the nuclear reactors were in the Manhattan Project making plutonium for the nuclear weapons program. And we're still working for fusion. Why I like it, it's very simple. The fuel is deuterium. One of every 7,000 atoms of hydrogen is deuterium. And tritium bred from lithium. So we have to get rid of all of our batteries because we need lithium for fusion. It's passively safe. There's no way fusion ever could run away. No way. There's the radioactive products of fusion are a neutron and helium. So there's no way, and it's 100 million degrees, so there's no way it could ever run away in any accident. It's hard to turn it on. It's easy to turn it off. Radiation products are not radioactive by nature. Deuterium and tritium goes to a neutron and helium with a 17.6 MeV energy release. This is a field burn of 10 to the 11th joules per gram, a big number. The neutron can activate materials, but they tend to be short-lived, and you can at some level have some construction of what they would be. There are some fusion reactors that actually have liquid walls, so the walls can be protected from structural damage. But of course, that's all great. Why is it? And it's how the universe powers itself, right? The visible universe has been fusion for 12 billion years or so. So it's nature's way of making energy, right? But as John Kennedy said, on Earth, God's work must truly be on our own. So it's hard. Fission is basically room temperature, right? Doesn't require anything in terms of heating it up. But fusion requires, to be able to overcome the Coulomb barriers, it requires 100 million degrees of temperature. So this is to get adequate reaction rates, and that is hard to do. The plasmas have to also be confined for a long enough time at a high enough density that you get some energy out. And the way of doing that, this was done by John Lawson many years ago. It's the product of the density and the confinement time, how long the plasma is hanging around. It's got to be 10 to the 14th centimeter cubed per second. And of course, this is all done with high temperature plasmas, which are fluids, electrically charged fluids, susceptible to many, many, many instabilities that go on and on and on. So it's very hard, and today no one has yet produced net energy from fusion in a controlled way. Okay, now, so my fusion colleagues I go to fusion talks, I give this talk, it's going to take a long time, and they get beat up because they always say it's 10 years away. We can do this in 20 years, just give us enough money. And that's not true. I don't believe that is true. It's too hard a problem for money to solve alone. It will take time and ingenuity along with money. So the way to look at that, plasmas of, Irving Langmuir did a lot of plasma work in the 20s and 30s, but that wasn't the type of plasma we're talking about. Physics of plasma, the first really time you could make plasmas which were thermonuclear type was really when you had nuclear bombs. That's the first time you can actually look at fusion in the, quote, the laboratory. And of course, people will use the fission analogy, says, well, we can do this real fast too. Fission was real quick, we can do fusion real fast. Well, it ain't that simple. But really, we've been doing the physics of plasmas for at least 60 years, and it'll probably and we'll go on and on and on. But this is, when I hear this is the physics of making, diagnosing, and understanding plasmas. And there's been tremendous work done on that, but it's not an energy producer. Now you get to the point where you actually will start having fusion. What I mean by the physics of fusion is that you'll now have fusion as part of the energy mix. All of the plasmas done here is where the plasma is heated, confined, whatever, by external energy sources. When fusion starts happening, fusion now becomes the dominant energy source of heating the plasma. And so this is the physics of fusion. And there are two facilities, which are, one is built in NIF, which is getting a lot of negative press right now because it didn't do fusion in a couple years after it was built. And that's crazy to think it could. I was very much involved in the beginning of this. And I always thought it would take a decade after the machine was up and running and understood to be able to see if you could make fusion. NIF eventually will do it, I still believe, but it's going to take another 10 years. But it exists. It's a fusion-capable facility. ITER and NIF is what's called inertial confinement fusion. Remember, I told you need an n-tal of a certain number. You can either do it with very high density and short time. That's how a nuclear weapon works, and that's how inertial fusion works. The plasmas in NIF are put at densities of 10 to the 26 particles per cubic centimeter. So that's 7 orders of magnitude more than the density of air. So it's a dense plasma. And the pressures are 200 billion atmospheres. So typically the pressures in the core of a star you make in the laboratory. So a lot of times people say we're making a star on Earth. It is. You're making the pressures and conditions similar to what's found in stars. But the confinement time is no confinement time. The confinement time is the inertia of the plasma before it figures out nothing is holding me, let me blow up. By that time, the fusion has taken place. So it's an inertial confinement. So the challenge here is assembling the plasma in that state. That's the challenge. This is ITER. This is magnetic fusion. Magnetic fusion is confining a low-density plasma for a long time. This was the ITER tokamak was actually developed by Soviets during the nuclear weapons program by Andrei Sakharov and Igor Tam. They invented the tokamak. And it eventually became the dominant configuration for magnetic fusion. Here you take a low-density plasma and hold around for a long, long time. The plasma densities here are 10 to the 14th particles per cubic centimeter, which means they're about 5 orders of magnitude less than atmosphere. And the pressures are typically only a few atmospheres. So this is a low pressure but high temperature plasma. This is a high temperature and high pressure plasma. This is built, this is under construction, it's an international project. It was the last remnant of the Cold War. This was done by Gorbachev and Reagan in Iceland. They agreed to do this. Soviet Union collapsed, U.S. got less interested, and now it's dominated by the Europeans and the Japanese, and with growing interest with China and India and other places. This will be about a $25 to $40 billion project by the time it's done. And this was around a $3.5 billion project to construct. NIF was built to do fusion, but also to support what's called Stockpile Stewardship Program, to support the nuclear weapons program in the absence of testing. So it develops codes, It validates people who are involved in nuclear weapons who will never test one in their lives. So NIF has a multiple dual purpose, whereas ITER is a single purpose energy machine. So over the next 20 years or so, you're going to see people develop and demonstrate fusion in the laboratory, but doesn't make power. Then the next 20 or 30 years is actually, this is where engineering and materials come into play. This is a very stressful environment, both of these do, and you're going to have to develop an engineering solution to materials and actually efficient extraction of energy and breeding of the tritium. You must breed. Fusion must breed. So this is what's going to happen once you have a fusion source to really look at it. And then after that, you'll start developing reactors. So fusion, anyone tells you fusion is going to be here in the next 20 years, they're smoking dope. And it ain't true. And I've been doing it for 30 years, but I still believe it is a worthwhile thing to do. When you sell programs, one of the questions you get asked is, you have to say it soon or else no one will fund it. All right? Remember, it started in 1950. That's 60 years ago. People will fund it. It's a challenge of the people who in the program to show that the vision is real and to be honest about the challenges. But fusion eventually will come. But one of the applications of fusion, and so it would be a very controversial one, but it connects it back to the fission program. Remember I said fusion is a Gen 6 reactor. What's a Gen 5? Well, for a pure fusion reactor must produce energy in excess of what was made to heat it and confine it, right? It's called gain. How much gain does the fusion system give compared to the energy that was used to make it? And that must be for inertial fusion, it must be about 100. And that's because the inefficiency of the laser and the process is so high, I need the fusion source to be 100 times more energetic than the driver of the laser here was. And that's because of inefficiencies. I want to be able to sell power to the outside world. This would give me a recirculating power of around 25%. So 75% of my power I could sell. In magnetic fusion, it's about 40. You need about a gain of 40 to be able to make a pure fusion reactor, to be able to sell about 75% to the outside world. But, and that's going to be challenging, even once you begin to do fusion. Just show you, ITER's gain is calculated to be 10. NIF's gain is supposed to be about 10 to 15, far from what you need for a reactor, a pure fusion reactor. However, what if I coupled fusion into a burning up actinides and coupled it with fission? That's controversial because people want to separate fusion from fission, but maybe the first application for fusion is to be connected to fission. And the reason for that is that the gain that you get to sell power, you do this, you destroy and make power at the same time, is a product of both the fusion gain and the fission gain. So the fusion neutrons here basically are enhance fission. So what you do, this is in many ways a step in the right direction. Without going into much detail, there's a lot of things that work this way. But it requires only fusion gains of around 10, which is what ITER and NIF will do. So you'll be able to demonstrate a fusion gain that if coupled to a fission system, you could actually get net power out and actually reduce waste. So this could be a way in the future of transitioning fusion. But it's very controversial and will only happen if fission is accepted more by everybody. And just to show you, remember, now you see my plot. So here's my plot of growing of fission power. Here's about 3,000, 4,000 gas reactors. So we're making US energy. And if I put my fission in here, I destroy the waste. So I need no repository. So if I reprocess once and do this, I need no repository. So fusion would be a way of ending the legacy of fission. So you think of it two ways. It's transition to fusion and ending the legacy of fission if you're able to do it. So it's a good thing to go. So summary, now we're going to talk about biofuels. So here's my time scale, right? This is going to take a long time. It's going to require both physics and tremendous amount of engineering. And we haven't really even reached the engineering phase yet. Comes from the private sector. You go ask a utility company to do fusion. They'll just, I tried with Paul Allen and Bill Gates. Even they wouldn't do it. And it's going to take both public and private investment when it's a lot more mature. Fission could be the bridge. There's a transition path. And again, long-term nuclear options are limited. Eventually, you will run out of uranium and thorium. So you have to use other fuel cycles. So you can either use fast reactors, which I didn't talk about, or fusion. So eventually, if nuclear is going to be our long-term solution, it's going to be one of those two. And I think it should be fusion. All right, biofuels. Well, now we're really going to change things here. I hope not make you asleep. Let's talk about biofuels. So we're always going to need hydrocarbons. I don't care how we electrify the planet. We're going to be flying in jets, and they're not going to fly in batteries. All right, so we're always going to do it. Just to give you a sense, jet fuel, about 16 billion gallons a year of fuel is used. So it's a pretty good sizable chunk. And the U.S. is about a third of that, as you can imagine. So my interest in biofuels was jet fuel. We do ethanol, I'll talk about that, but it was jet fuel because jet fuel is something which is you can't replace with any other energy source. So of course, guess what? The DoD is interested in this. By now you see, find a national security mission to push an energy portfolio or agenda. So the DoD wants by 2025 to be 25% of its energy is renewables. That's pretty good. It's California. That's what California wants to do. And so here you're going to have a motivation from the DoD to transfer all its energy sources to be a quarter renewables. So they're pushing biofuels. They're pushing some nuclear. They've been a nuclear player, as you've known, for a long time. Even the Department of Navy wants to reduce it by 50%. So they really want to eliminate or they want to transition into alternative energies faster than the private sector would. And you'll see there's some opportunities that the DoD is doing to make that happen. All right? So to me, you hear me talking about energy density. Remember, fusion is 10 to the 11th joules per gram. Biomass is about 8 to 10 gigajoules per square meter in a year. So it is an energy density issue. So the challenge to me in biofuels, I know you guys do good, some of the research here is in cellulosic biofuels, good stuff. But to me, the challenge is densification of getting this into 45 megajoules per liter. That's what jet fuel is. So I got to somehow find that and get it into that. And to do it at a scale and cost that's competitive. The other thing with cellulosic feeds, with not only is the energy contained, it's just distributed. I mean, we can't grow hundreds of tons of biomass in an acre. This is, great farming practice will give us 10 to 20 dry tons an acre. That would be a big stretch goal to get. So what that means is if I want lots of jet fuel, I'm going to need lots of acres. And remember, food and fuel are competition always, and water. But the DoD was interested in this because they want to transition their air fleet to JP-8. And JP-8 is the logistic fuel in theater. So if you're in Afghanistan, you're driving a truck, it's on JP-8. So jet fuel is what everyone uses when you're in theater. So there are several ways of doing this, right? Everyone knows about corn ethanol. The U.S. has about a 15 billion gallon a year capability in corn ethanol. And we're not going to do much more than that. Almost half the corn grown in the United States is used for making ethanol. Brazil has a lot of sugar cane. They do a lot of good things with that. A lot of biofuels will be done in the southern hemisphere. So we looked at cellulosic biomass, things that would not compete with food, would be acceptable in terms of land and water use. And there's a study that's done about every several years. It's led by Oak Ridge National Laboratory. It's called the Billion-Ton Study. And it's basically, does the U.S. have enough biomass to make a significant impact to our energy use and transportation fuels? We use about 160 billion gallons of fuel a year, not all in transportation, of course, heating oil and transportation, or both of that. I don't know what I do. Hopefully I'll go away. What the hell is this? Uh-oh. I didn't steal it, I promise. So here's some bagasse here. There's a lot of biomass up there. This is a spectrum of, I'll blame you guys for this. This is on tape. This is distribution. There's a lot of cellulosic stuff from energy crops, from corn stover, agricultural residue. About the equal amount of mass when you take corn to eat is left on the ground. That's corn stover, and you can take some fraction out of the way to make fuel. That's what a transition will be in some biofuels. Municipal solid waste, it's a good thing. Every time I see a half-eaten sandwich, I think jet fuel, and of course wood. So we at Logos have a program with DARPA basically to look at making jet fuel out of all these materials. And again, you have to, this $1 billion studies, and I've sent it around to people, I'm sure many of you have it to do biofuels. You have to look at impact on food, water, land use, and it's got to have attractive economics. And that doesn't exist right now. To me, there are only 2 feedstocks today that can satisfy to be an entree into the biofuels. And that's actually the wood industry, because you collect and transport wood already for pulp mills. You'd have them around here. And municipal solid waste. It's already collected, and the biogenic part of it, and people will actually pay you to take the food, or to take the waste. All right, so what happens next? Uh-oh. That's not working. What's going on? But here it is. So I'm a big fan of MSW as an initial feedstock for biofuels. Now I like history. It's the landing at Normandy. It's not going to Berlin. It's not the end of the war, but it gets you started. And why is that? So why is MSW attractive? Well, there's a lot of it. It's already got a reasonable collection infrastructure. You have to sort it, but it's got a reasonable. People pick up trash. We sort it at my house a little bit already, and a lot of places in the world are doing that more and more. A lot of it's near military bases, so you have the chance of getting the supply chain getting to the end user quickly. It's not dependent to first order on drought. Remember, there's a lot of drought going on right now. Look at the price of corn. Look at the price of of beef, because 60% of the country is in drought. Well, people are still going to eat, and so you're at the back of the food chain, so you're still going to get the crap. So you're not susceptible to those types of the seasonal variations, and then of course drought. It's a great technology. I like it because no one wants a landfill in their backyard, right? So let's reduce the landfill. It goes in the landfill. Let's take the biogenic material and turn it into fuel. Don't make methane. People try and recover methane now. That's one thing. If not, it's methane is a pretty potent greenhouse gas, about 27 times that of CO2, but it doesn't stay in the atmosphere as long. But nonetheless, you don't want to do it. And you want to prevent the leachate, basically the contamination of the groundwater from biogenic material. And you actually, in many parts of the country, you get paid to take it. So instead of having to pay for the feedstock, instead of having to pay $100 a dry ton for corn stover, someone will pay you $35 or $50. They'll pay you to take the feedstock. So it's like a co-product in some fashion, if you want to look at it in some ways, if people look at biofuels. And there's enough to bake maybe a little bit less than 1 billion gallons a year in the country. So it's a way of getting started. And this is just an example of what that looks like. So one of the things that we have done is looking at studies of what is the scale size. And again, it's so much driven by feedstock. And to give you a sense, a 25 million gallon a year plant is roughly 1,000 tons of feedstock a day. So you have to have trucks or whatever carrying that much material in. So that's a big logistic. You have to look at the logistics issue of biofuels. Is not simple at scale. And remember, this is a small, 25 million gallons a year is a small plant, but it's going to probably be the sweet spot for what these plants are going to look like. At 100 million gallons per year, it's 4,000 tons a day. That's a pretty daunting thing when you think about it. Every day you have to bring 4,000 tons of crap in. So we spent a lot of analysis looking at what the cost of production for jet fuel would be. This is with actually food waste as a dominant source. We've done it obviously with other cellulosic materials. And it's just a way of what would be the production cost. So actually it looks pretty good when you get above 25, 30 million gallons a year. You can produce it for about $1.50 or so, $2 a ton, a gallon. And that's because you're getting paid $35 a ton to take the food to waste. If you have to pay $100 a ton, you have to think about, you have to add another $1. 70 gallons per ton is a good number for fuel. So I got about $1.30 just in my feedstock cost to add to this, so I have to pay for it. So but that's one of the challenges it is one of the challenges of biofuels. I think anyone who looks at this hard comes away with this thing. We won't have 100,000 barrel per day refineries. We'll have 25 million gallon a year refineries spread around the country with different feedstocks. Now making jet fuel is real difficult. We like jet fuel. The DARPA likes jet fuel, so I like jet fuel. It's really difficult. Here's biomass. It's lignin, hemicellulose, and cellulose. You got to break this down into sugars that you can ferment. And jet fuel is a very complicated material. It's got a lot. This is the carbon number. This gives you essentially relative distribution. Jet fuel is sort of carbon 8 to 12. Diesel's up here, gasoline's down here. And it's got a range of molecules that they're there for reasons for freeze point, flash point, and lots of things. You got to be really safe with jet fuel. So it's a hard thing to make. Here's give the density is about 8/10 of a kilogram per liter. The flash point heat capacity is about this, so the energy density is about 43 megajoules per kilogram. Flash point is 38 degrees C. Freeze point is this. So whenever I fly to Europe on a polar route, I look outside with the air temperatures. I get worried now. I never used to get worried if it's too cold, because of course it won't. But it's now something I look at. But jet fuel is a hard thing to make, and so our program has been to make that out of cellulosic material. So there are many ways, and I'm sure many of your researchers know, there are many ways of making biofuels. There's biological ways, there's chemical, thermal, there's different products that come out, and then you have to, of course, upgrade into the right fuel. Our program looked at all these different ways. I'm not going to talk about them I'm going to show one as an example, but we looked at lots of different ways of doing it. This is something that's called mixed alcohol oligomerization. This is one of the pathways we looked at that actually looked very attractive. Takes biological waste, pre-treats it, it ferments it, makes organic acids, it makes ketones, I'm a physicist, so to me, matter is made out of protons or nuclei and electrons. All these molecules drive me crazy. I never had to worry, was it Kelvin or Celsius? It didn't make a difference to me. Now it does. So I got to be careful when I say what the temperatures are. But a lot of different steps here. Some of these are traditional chemical engineering steps, refineries, out comes out jet fuel, and of course you make all the different things. So we did this and actually made a lot of jet fuel. You don't have to look at this, but there's a lot of specifications for jet fuel. Don't look at that. The only thing is that the things that counted, these are the ring molecules you have to have. It's got the heat of combustion. We actually made very good jet fuel out of crap, and it worked. And it's nice and transparent. It smells like, my people I work with, they smell it, says right, it looks fine, it's good. They just smell it. I'm used to different types of measurements, but looks and smells right, it's okay. So they understand these things. Now there is an opportunity, and this again, by now the theme. Can the government help you commercialize things? So there is a thing going forward now called Title III. So we made jet fuel, and there's other people who have made jet fuel. The question is, how do you commercialize it? Well, here's one way in which the government can help you. And it's actually an interesting one. By now you know I like history. I'll give you a little background as to why it is. This is our Mr. Obama, not with Mr. Romney, so he was good here. Georgetown a little over a year ago. And he's telling the Navy, I want you to make jet fuel, and I'm going to give you an opportunity to commercialize it. And it's a thing called Title III. And it was a combination of the USDA, DOE, and the DOD. Mostly the DOD is driving it. So what's Title III? Anyone hear of Title III? All right, someone, I knew you would. What it was, actually, a little history here. It's 1950. What's going on in 1950? The Korean War. World War II had ended. The United States had demobilized militarily. Everyone's tired of war. And we have nuclear weapons, so we're not going to have a war like we did before. So we can we can reduce our conventional forces a great deal. Well, Stalin never did that. He just was always worried about another invasion from the West. So he never really demobilized, even when we had tough economic times. So the Korean War starts. The Cold War now has proxy wars. And so the Russians are flying for the North Koreans, are flying MiGs, and we're fighting with them P-51 Mustangs from World War II. Because no one was making jet engines. So I said, we need to make jet engines, and the commercial market is not yet here. So let's have a way in which the government can help. So it's out of the Defense Authorization Act. You see the time, lots of different titles. But this one was to basically set up an opportunity to build, to commercialize things that have been made that the commercial market is just not ready to do. And what it does, it stimulates private investment by paying up to half of the cost. So if I want to build a biofuels refinery that costs $200 million or $300 million, the government says, I'll pay $150 million for it, and it's yours. But I want you to build a plant. So it allows you to basically, if you will, help cross the valley of death from an idea to commercialization. It's a great idea, and it happens sometimes, and this is an example, it's going to happen in biofuels. And DOD is the only agency to do it, of course. DOE doesn't have that authority. So what it will do, it will take lab scale, pilot scale, to commercial scale. And what is going on in fourth now, and I'll show the Title III in a second. I think I have it this may be the last one. It's going to allow you to, the government will contribute half of the capital equipment for this, and also will it will buy your product. An organization called the Defense Logistics Agency buys fuel for the military. It will give you a 10 or 15-year contract for your product. What more could you ask for? Here's the market, I'm going to build the capital for you, help you. So my hope is that this will go forth and actually help cellulosic biofuels, particularly these jet fuel and diesel, become commercial. And there'll be an announcement of awards probably within the next month. So here's my summary of biofuels. There is a potential for large scale. We'll never replace all our present use of petroleum, but we can have a big chunk of it over the next century. And hopefully with more efficiency, this will be a bigger fraction of our needs. I think many promises show promise in early demonstration pilot plants. They do. I showed you one. Not a lot of detail, but I showed you one. I like jet fuel because two things. One, the government's interested in it, and the government will pay. And secondly, there are international motivations. Right? Europe, if I land a jet in Frankfurt, I'm going to have to show I have a reduction in its greenhouse gas compared to petroleum of 20%. So they're going to start, jet fuel will be, international regulations will impact what we do, and politics in Europe are going to affect what happens to jet fuel, or politics in other places. So, of course, U.S. and China are fighting that, but you're going to see international pressures to have reduction in GHG on jet fuel. So biofuel is a way of doing that. The feedstock to me is an absolute major challenge for scale up, both the cost and volatility. There was a thing that the National Academy of Sciences did a study about a year ago, a little bit less, of the, is there enough feedstock? And the question, and what will it cost? They had a nice table that said, what will a refiner pay for feedstock, for his economics, and what will a grower take for his feedstock? Well, the refiner said, we want 25 bucks a ton, and the grower said, 100 bucks a ton. So there's not an economic match there. So this is still an issue to get the cost of feedstock to be viable. Scale is going to be limited by the infrastructure necessary for delivering the feedstock. The plants are not that big from a chemical engineering standpoint. The feedstock, the logistics will determine it. And to me, MSW and Wood today are the ones that can support 10 million gallon a year plants today if they were funded. And Title III presents a great opportunity for commercial demonstration. The DoD wants, by 2016, they want to buy 10 million gallons of jet fuel a year. So hopefully this will lead to biofuels, at least in this thing taking off. And I think that's it. But what's it going to, here you go. I showed you this at the beginning. What's it going to look like in 2100? Some of your professors should give you a quiz. Map out what the energy use in the United States is in 190 years from now. See what it looks like. And that's the end, I think. Yes, that's it.
Questions from the audience? Go ahead.
What's your estimate of the energy return to energy investment? Biofuel scenario that you're talking about.
You want the energy investment? It's going. I mean, one of our requirements is basically to have at least 50% energy efficiency. So that's a demanding thing, but we've been able to do that. So 50%. You'll get 50% of the energy back. That was in the original biomass. You'll get about 50% of the energy out of it.
I had a question regarding the economics of getting the municipal solid waste.
Yes.
It seems to me that if you establish a chain through which they can get rid of it, ultimately they'll smarten up and start charging you for it because you'll have a big plant just waiting for the stuff and you'll be stuck. So the economics that you presented is not exactly what you can expect in the long run.
My answer to that would be, I thought the same until the partner we're dealing with was the waste companies, and they will give 10 to 15-year contracts with tipping fees. So you're right. In the future, anything that has value eventually is going to cost something. But there's also a lot of there are a lot of other costs. They still make money by paying you. They still collect money, by taking. No one, I think, it'll be a long time before someone gives me a check to pick up my garbage. Right? That's what we're talking about. But no, the economics will change over time. But again, that's why I say it's a start. Today, it's a start, and I think you have to show this at scale that it'll work.
Any other questions?
I wonder if you could comment about your position and your feeling on algae as a fuel source. I know that there's a great deal of work going on, and there's supposedly a commercial plant, a small commercial plant in Southern California.
Right.
Using brackish water. They also have some strains that can use seawater. And the attractiveness of this process is the very high yield of fuel from a small amount of land relative to other biofuels. So it is not as land intensive. I wonder if you'd like to comment.
Yeah, no, I mean, DOE did a study a long time ago, as you know, which was one of the motivation of how many thousands of gallons per acre a year you get out of algae oil. It was typically 3,000 to 5,000 gallons per acre a year is a number I remember. Something that, what theoretical limits in some fashion you would get. Cellulosic stuff, of course, with this is probably closer, if you figure you're getting maybe 1,400, if you're lucky, maybe 1,000 gallons per acre a year for a cellulosic source. So you're right, so you have a factor of maybe up to 4 or 5 better. So I'm skeptical of algae at scale. I mean, there's only parts of the world where you can grow it, as you know. Not every place can grow it. Whenever you do the economic analysis, it's always the co-products or the driver. If you look at, when does it make sense? The algae oil, I mean, you'll get 20% of the animal into oil. the rest of it, the raffinette, what do you do with the raffinette? So when people always do economic analysis, it's, the real benefit comes from you're going to make animal feed or fish food, which is, I think, reasonable things to do. So I think there's some, I never say never anything. I thought that, I like the cellulosic because water, a lot of things were positive. Algae, and you don't need co-products to the same extent you do with algae. So if you're doing a program, if you have several commodity markets, you have to sort of figure out how they work. It's a tougher problem. And algae, you have to look at the commodity market and other things. And so if I had to choose, I'd say pretty good, but I still wouldn't spend an infinite amount of money. There's a lot of, almost as much PR on algae as there is on fusion at times. It's so much land use reductions and the like. But when you look at other water use, if you brackish water, you still evaporate all the time. The ponds are pretty big. I mean, the biggest algae farm, I think, is one in Malaysia going up now, which is the largest one in the world. I can't remember how much it is. It still was far less than what was required here to make the jet fuel. So the land use is better. It's somewhat better. The water use is intense, as you know, but if you use the right water, I mean, there's many more gallons per water. Another good metric for biofuels, how many gallons of water did it take to make the gallon of fuel? That's another good metric, not only just how much energy efficiency. And algae tends to be much higher than cellulosic, even though it's, as you would say, a lot of times it's not good water. But it should be done. There is no one solution. There's not enough cellulosic feedstock to support all the transportation needs in the country. There's just not. I mean, we transformed agriculture over a century. We had 50% of people working on farms in the beginning of 1900, only a few percent now, and we have a lot more people and a lot more food being produced, so much more efficient farms. That will take that century to transform a cellulosic energy agriculture to do that. And algae should be part. And actually, the raffinette could be part of. We could use a raffinette for cellulosic feedstock too. So it's a rambling question, but it should be looked at, and people are looking at it. We didn't. Hawaii likes it very much. Yes.
My understanding of the way people produce bioethanol is because corn in the ethanol production really occupies a lot of cost, and also the net energy gain of corn ethanol is lower than cellulosic ethanol. If you provide jet fuel by bio, I think in the later process, because you need carbon 13 or carbon 12 or carbon 14
Right.
fuel, you need to put a lot of extra energy into the process. So I'm wondering, is it worth producing jet fuel or biofuel or just to use?
Well, that's the question. So we go through all that, and so we use about 50. We get about 50% energy recovery from all, and that includes all the energy to make it too, not just the energy in the biomass, but all the energy used in conversion. So it still can be economic. You're right. I mean, ethanol, but ethanol only has 60% of the energy density, of the other hydrocarbon fuels. It has water issues. I mean, it's useful to do. I drive an E50. I drive the E85, whatever the hell it is. But you're not going to fly a plane on ethanol ever.
I invite you to speak to our guest if you have more questions. Thank you very much.
Thank you. Yeah.
I wanted to thank you for coming. It was very nice of
that
you. and very
entertaining? I hope that was
informative.
entertaining.
It was.
There we go.
All right.
Thank you very
You
much.
have your computer.